All right, welcome to Math 331, lecture 23. What we're going to do today is we're going to do some problem solving related to Project Euler, which is an absolutely wonderful website where the problems are, for the most part, absolutely trivial, but non-trivial if you want to do it before the universe dies of heat death multiple times over. And that's the challenge, is how do you look at these problems and then code them efficiently? So sometimes it's writing good programming, sometimes it's using some good theory to reduce. So the first one that was suggested was problem number 16. This means I have not changed the size of my pen. Okay, so we have 2 to the 15 equals 32768, and digits sum to 26. What is the sum of digits of 2 to the 1000? So can somebody give me a trivial way to solve the problem?
Just brute force it.
Brute force it, okay, right? So one solution is brute force. There are certain things you need to know, and because we have at least one computer scientist in the class, approximately what is 2 to the 10? 1,000. It's approximately 1,000. So when you think about the prefixes, megabytes, gigabytes, it's supposed to be a factor of 1,000, but in computers, base 2 is so wonderful, and 1,024 is so close to 1,000, we will say stuff like this. But if you're actually looking at very large downloads, you can see the difference between a gigabyte is not 1,000 megabytes. So let's get a sense of how bad. So 2 to the 1,000 is 2 to the 10, right? To the 100, right? So that's going to be 10 cubed to the 100 is 10 to the 300. The number of subatomic doohickey thingamabobblejigs in the universe is around 10 to the 90. If everything in the universe were a universe, that gets you to 10 to the 180. So to give you a sense of if we actually wanted to write down this number, right? So universe has less than 10 to the 100 subatomic stuff. A universe of universes is 10 to the 100 squared, which is 10 to the 200, which is so much less than 10 to the 300. What does this tell you about our chance of brute forcing this on the computer? There's no way you're going to be able to write down the number. Now, you could just maybe compute it and have a formula for each digit and then just keep adding it as you go. But to actually compute this number and write it down and store it, if every subatomic particle was a universe and every subatomic particle there was devoted to your use, you could not write this down. So this is enough to tell you that there's no hope in hell of computing the number by brute force.
Can't we store a number more efficiently? We don't have one particle in the universe represents one.
Sure.
So
I'm saying if we wanted to write them down, if you use each particle to write down a digit just physically,
yeah.
does this give you some sense?
Yeah.
And again, there's efficient ways to store things. We're just trying to get a sense of if we wanted to write this down and look at this number. And again, yes, if you use binary, which is in some sense what we're doing here, you can represent huge numbers by just writing numbers in binary with just zeros and ones. But if we want to physically see all the digits and just physically write them down, we can't do that. So how would you attack a problem like this? What's your first thoughts? And if you haven't done this problem before, this is a chance to think about it. How would you attack this? What would you start to do? Yeah.
I might just write out smaller numbers.
Absolutely. Gather data. hopefully there's a pattern. Maybe every time we increase by a certain number, we basically like add one or something like that to the digit sum. Wouldn't that be wonderful if we had something like that? So we could have, now we're doing 2 to the n. So maybe we start with, we have maybe n, 2 to the n, and then the sum of digits. What's the first n we should look at? Maybe 0. I don't know if we should start with 0, but why not? Let's start with 0. 2 to the n is 1. The digit sum is 1. Then we could have n equals 1. We would have 2. The digit sum is 2. Then 2 would be 4. The digit sum is 4. 3, 8, 8, 4, 16, 7, 5, 32, 5, 6, 64, 10, 7, 128, 11, 8, 256, 13. Anything look good at this point? So n, 2 to the n sums. We have to keep going. So we have 9, 10, 11, 12, 13. So 9 would be 5, 12, would be 8, 10, 24, 7, 20, 48, 14, 40, 96, 19, and then 8, 1, 9, 2, I believe, 20. So are we noticing anything?
I don't see a clear pattern.
I don't see a clear pattern yet either. And so it could be that we have to go even further before we start seeing a clear pattern. One possibility is, are there ways to separate, digits so that they don't interfere with each other? If I know the digit sum of 2 numbers, do I know anything about their products? So again, right now, we're trying to figure out what can we glean from the data. So if I give you 2 different n's, do I know anything about what happens when I combine them? If I take n equals 2 and n equals 4, then that's 4 times 6. 4 times 16, which is 64. So if I try to do something like that, if I take, say, 4 and 16, and that would get me 64, the digit sum is 10. 4 plus 7 is 11. If I take, 2 4s, 16 times 16 is 256. Is there anything nice? Is it one less? Is there anything we can say?
Not one less because 8 times 8. It looks like it's one less of the.
So is it one less than?
The sum of digits, like if you're multiplying together. Or at least in those 2 cases described.
So 32 times 32 would be 1024, right?
Mm-hmm.
And 5 and 5 is. Now we also know that 2 to the n is 1 more than 1 plus 2 plus, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. Is there any way to break these things down nicely? When we're looking at the sums of the digits, we don't care about how many powers of 10 there are. We just care about what the digits are. So if I give you 314, it's just 3 plus 1 plus 4. It's not 3 times 100 plus 1 times 10.
I mean, we know that the last, like the ones digit.
Good. So we can figure out what the ones digit is. Can we keep doing this to figure out now, again, this is going to be a number with, on the order of 300 digits. We can look at this, modulo powers of 10. Does this have to cycle? If I just look at the last digit, 486 4868. I'm sorry. Let's just look at the last digit of the number. Sorry, it's 2486 2486 2486. Okay, so we're seeing the cyclic pattern there. What about the tens digit? So then we have 13625 12499. So if it cycles, it's going to take a longer time to cycle. So this is definitely one possibility. If we knew something about how numbers combine, 2 to the 1,000, we could write that as 2 to the 100 to the 10. Can we somehow figure out what happens to your digit sums in something like this? So if I give you a number and I raise it to a power, do we have a formula for what happens to the digits? The problem is you have all these terrible adds and whatnot.
They're terrible, sorry.
So if I give you a number like 314 squared, that's 3 times 100 plus 2 times 10 plus 4 squared. I'm going to get 3 squared times 100 squared plus, and then just all the different cross terms. And so the question is there a power of 2 that's going to be really nice and easy to work with? If I convert something to base 10, 2 to the 10 is 1,024, right? So, what if I started saying, well, I know 2 to the 10 is 1,024, so 2 to the 1,000 is 1,024 to the 100. Is there a nice way to get a smaller number and a smaller power?
We want to reduce it to 100 or 10.
So I know for a lot of calculations, the method of repeated squaring is really nice. And so if I want to calculate something, I can cut down on the number of computations by squaring and then squaring the square and then squaring the square of the square and so on. I'm not worried about doing 100 calculations per se. I'm just worried about the size of this in terms of just keeping track of something that's this large. So it seems like there's got to be some kind of formula that allows us to keep track of what's happening with the sums. And there should be some nice expression, maybe every time we go up by 10 or something like that. So Pedro, did you notice something nice for this problem?
I think we can maybe try these binary numbers for this.
Okay.
Right.
I mean, well, I mean, 2 to the 1,000 binary is just 1 with a bunch of zeros.
Yeah, I mean, I'm not sure if that would help.
But I mean, that's the whole point, is to, you know, to explicitly write it down. I mean, it is. Oh, wait, or maybe I was being absurd. It's only 300 digits. It's
That's
only
what I was
300. Oh yeah, it's only 300 digits. I'm sorry. Right, it's only 300 digits. Sorry. Ignore what I said earlier. It's only 300 digits. So I think I was making this problem too hard because I was thinking, but if it's only 300 digits, we can store this as an array. This is not horrible. And so we could just brute, yeah, I'm sorry. We can brute force. I just got confused in looking at this as, you know, it's not 10 to the 300 digits, the numbers of size 10 to the 300. It's only 300 digits. So if it's only 300 digits, that's not too bad. And then what you could do is, if you want to do things like repeated squaring, you could do, you know, 10 to the 24 to the 10th, you know, to the 10th if you want, and just make things a little bit easier. Or if you want to go, and you could keep, you know, playing games. But if you just have an array, you can just keep updating the array elements with, you know, what you have. And so something of size 300 is not terrible. Is there a better elegant solution to this? I mean, it feels like there should be. You know, is there just some pattern or some structure? The difficulty is we're trying to pass from knowledge of the number to the knowledge of sums of digits. Do people know divisibility rules? You know, when is a number divisible by 3? When is a number divisible by 9? Yeah, so if, you know, the sum of digits is 3 or 9 is divisible by 3 or 9. And so if I give you a number, I can reduce the number to something smaller that has the same digit sum. And that will determine whether or not it's a multiple. So for instance, if I give you 429, this is the digit sum is 15. And that's still going to be divisible by 3. The problem is, if I want to check to see if it's divisible by 3, I could do another digit sum. But that would just be the sum of the digits of that. That would not be the sum of the original number. And so there's lots of, you know, really interesting rules for divisibility. The only one that's really difficult is 7. 11 is a fun one, which is the alternating sum. So sometimes for problems like this, you know, are there any interesting games you can play? Is there an interesting factorization? Yeah, I'm not seeing how to do this other than brute force, which I don't like, because if they replace 1,000, I mean, I guess even with 1,000,000, we could do 1,000,000. We can have an array that large. That's not too bad.
Are these problems designed to be done like pen and paper or?
No. These are designed to be done by computer for the most part. But a lot of them, you can write an inefficient computer code for small values, but if they change the parameter, then the code won't work. we could brute force 1,000. You know, it's easy for the computer to just keep multiplying. Even Mathematica can just keep track and store that. And then just, sum the digits. But if they gave me, a trillion or a quadrillion, it's, how many operations can the computer do? So I guess for this one, I'm not seeing anything better than just brute force.
Sure, by inputting that sequence that we got.
Onto, sure. So I'll go to the OEIS.
It'll probably recognize it as the.
As the, right. But sometimes it has interesting observations. All right, so the digit sums. All right, so it was. So it was 1, 2, 4, 8. And we're sure these numbers are correct. 7, 5, 0. Oh, no, sorry, 10. 10 was the next digit sum. 10, 11, 13, 8, 7, and we'll do 14. So it's the sum of the digits of 2 to the n. So Project Euler is not showing a nice formula. It says it's believed that a to the n is asymptotic to n times 9 times the log base 10 of 2 divided by 2, but this is an open problem. All right. All right, so it looks like this might just really be a brute force problem. And the difficulty might be if you're using, say, an old program, you might not be able to use integers larger than a certain amount. And so the issue here might be, how do you deal with a 300-digit integer? And one way you can deal with stuff like this is you can use arrays. So if I give you a of n, then a of 0 is the ones digit. Or do you want to start off with 0 or 1? I know there's a lot of issues with how you want to index. Because I like 0 because that's 10 to the 0. And then 1 is going to be 10 to the first. So I would index like this.
Yeah.
And then A1 would be the tens digit. A2 would be the 100 digit, and so on and so on. And if I write my number as an array, if I multiply by 2, I can define multiplication or addition by just corresponding operations on array elements. And so the whole point of this problem might be, if you are in an environment where you can't have a 300-digit integer, you just have to do things by arrays. And so like the famous 3x plus 1 problem, it's very easy to do the 3x plus 1 problem with arrays. Is everybody here familiar with 3x plus 1? I apologize then for being the one to introduce this to you. There are 2 quotes about the 3x plus 1 problem that I love. One is by Erdős, who said mathematics is not yet ready for problems like this. I think the other one is Kakatani, who described it as a Soviet conspiracy to slow down American mathematics, because it seems so simple. And so the idea is you take a number, an, and an plus 1 is going to be 3an plus 1 if an is odd, and an over 2 if an is even. So someone give me a positive integer. 2. So 2 is even, so 2 goes to 1. 1 is odd, so it goes to 4. And then 4 goes to 2, goes to 1, it cycles. Somebody give me another positive integer. 12. All right, so 12 is even, so 12 goes to 6, goes to 3, odd goes to 10, 10 goes to 5, goes to 16, goes to 8, goes to 4, goes to 2, goes to 1, goes to 4. What would you conjecture with 2 data points? Yeah, it's always going to cycle to 4, 2, 1. And so one way to look at large numbers like this is to use arrays. If you want to do division by 2, you could look at your numbers in base 2 rather than base 10, which makes division by 2 much easier. So it's just, shift. Or if you want to do things in base 10, one way to divide by 2 is you multiply by 5, and then you shift. So either way, either of these ways would work. All right. Well, what's another Project Euler problem that people found interesting? And this is related to number 14 is the longest callout sequence. Which starting number under 1 million produces the longest chain? 27 is known historically for having an incredibly long sequence before it iterates to 1 relative to its size. I believe it's over 100 terms before it actually iterates down. This is a wonderful problem. This is the 3x plus 1 problem. What's nice about this is that it's completely deterministic. I give you a starting number, and the rule is clear. We don't know how to solve this, but what we can do is we can look at a probabilistic analog. How often, so if you're odd, 3an plus 1 is always going to be even. So after you multiply by 3 and add 1, you always divide by 2 at least once. What fraction of even numbers are divisible by 2 but not 4? Half. What fraction of even numbers are divisible by 4 but not 8? A quarter. So what you could do is you could say, let me model this and take a large number, and then half the time after I multiply by 3, I'll divide by 2 once. A quarter of the time I'll multiply by 3 and divide by 2 twice, and so on and so on. And I'll just simulate this. And if you do, that describes the behavior beautifully. It allows us to make conjectures about how long it should take before it converges to 1. It makes how high do you expect to get from your initial starting point. You can do some really great modeling on this problem. And so it's a completely deterministic problem, but these random ideas will allow you to get a real feel for the generic behavior. It's not going to be a proof. So when I do things like Math331 probability, I love to talk about stuff like this. How can we model something where we can actually analyze things? I can analyze these random variables. I can't analyze the number theory here, which is embarrassing as a number theorist. Anything else from the Euler that looked really interesting? So you were talking about the summation of primes. So this was number 10. Did you have a way to do this other than brute force? So number 10, sum of all primes up to 2 million. And since 2 million is prime, I don't have to worry if it's up to, including or not.
All the obvious ways to optimize it for checking up until the square root of the number.
Good.
Maybe better ways to keep track of your primes and do this method. I forgot what it was like a seed.
Right. So one of the things we know is we know that the sum n goes from 0 to say big N of n is big N plus 1 over 2. So this is a famous formula. And one of the ways you can prove this is if I give you 0 plus 1 plus ... plus big N, and I write them in reverse order, we see each one of these adds up to n, and we have it n plus 1 times. So if this sum was Sn, and this was Sn, we get twice Sn is equal to that. So one possibility is I know what the sum of all the numbers are up to 2 million. What could I do?
Well, subtract from there, but I don't see how it helps us.
It might not. And again, not everything we do has to help. I'm just saying, what are ideas? What are things we could try? It might be that the best thing you can do is to do some kind of sieve and find all the primes up to 2 million. So, one solution is just find all primes up to 2 million and add. Another thing is I can throw away all of the sums of multiples of 2. Right? And then I have to add back 2 because I want to keep the original one. I can then throw away all sums of multiples of 3. Then I would have to add back all sums of multiples of 2 times 3 because I removed them too many times. So you could try to do an inclusion-exclusion. But probably too much work. So
Can we estimate the number of primes less than?
So pi of x is defined to be the number of primes less than equal to x. And the prime number theorem says that this is approximately x over log x. So percentage-wise, the limit of numbers goes to 0. The percentage of numbers that are prime goes to 0. But there's still a lot more than squares. So there's a lot of primes. So the key observation which you made is that if M is composite, M has to be A times B with A and B greater than 1, and if A is less than equal to B, then A is less than equal to the square root of M. So if any number is composite, it has to have a factor at most square root of itself. So if we want to check to see if a number is prime, we only have to look at factors up to the square root of that number. So then the question is just, what's the most efficient way to go through and check and see which numbers are prime? Mathematica has a built-in function of prime n, which gives you the nth prime number. You could use something like that, but how do you calculate something like this? And this gives us an opportunity to talk about how do you want to do the calculation. One way to do the calculation is for each number between 2 and 2 million, I check to see if it's prime. Or I just look at the entire grid and I throw away all the numbers that are not prime, and I throw away all multiples of 2, all multiples of 3, all multiples of 5, etc. And so 2 million is such a small number, the square root of 2 million, that's not that much more than 1,000. So the number of calculations you have to do, it's not great, but it's not terrible. And you can throw away, a good chunk of numbers quickly. But, I would probably find all the primes up to, maybe like 1,414, something like that. Because if I have a number up to 2 million, it's got to be divisible by something up to that point. So the question is, what's the best way to do this? So if you give me a number, I can easily check and see, is it divisible by my list of primes? And I can have in my data file, here's my list of primes. And I'm talking about less than 2,000 entries. That's a negligible cost to have a list like this. But I have to check every single time. If I want to look at all 2 million numbers, what I can do is initially I can take an array. And so let's say I have my primes, 2, 3, 5, ... P max, where P max is the largest prime less than 2 million. And now I have my array. And what I can do is maybe, A of n equals 1 for, 2 less than equal to n less than equal to 2 million. And then for each prime, set A of, KP equal to 0. K goes from 1 to 2 million over P. And now I have an array which has 1 only at the prime numbers that are left over, and everything else is going to be 0. There will be some numbers that will be set to be 0 multiple times. That's fine. And now I just have to compute, the sum of n, an. And that will give me the sum of all the primes at most 2 million. Because an is now just going to be 1 only for the primes. So for this, I need one list or array of size roughly 1400, not too bad. And then I need something of size 2 million. All right, something of size 2 million is not too bad. This should be doable. But again, I'm interested, because I know some of you have looked at these problems. Does anybody have another way that they would attack this problem?
Maybe keep a list of primes,
Okay.
and then with each iteration of n,
Right.
segment here, you add like 1 to each element of the array. I'm not sure.
No, I don't think that helps. So again, this is not something that's going to scale well. But the primes are both random and structured. When you look at a very fine level, we don't know what's going on. We have rough asymptotics as to what's going on. We have rough formulas, but to get exact values is really hard. And so for something like this, there's not a nice formula. There is nice formulas for sums of arithmetic progressions. So if we try to play these inclusion-exclusion games, we know, formulas for the sums of, consecutive numbers. We can take a formula like that, and if every number is now in an arithmetic progression, multiples of 2, multiples of 3, multiples of 5, we just multiply by 2, 3, or 5, not a big deal. And we can play these inclusion-exclusion games. And then you can ask, what's the maximum number of factors you can have for a number that's less than 2 million? Well, to some extent, the worst case would be is if you're all 2s. Okay, well, that's not such a big deal. If you have distinct prime factors, have you ever heard of the primorial? So n, like this, and this is not a social media post or anything, is read n primorial is the product of all primes at most n. So for instance, 5 primorial would be 5 times 3 times 2 is 30.
My grandpa likes asking people who he meets for the first time if they can prove that there are infinite number of primes. You can do it n primorial plus like all known primes plus 1.
Yes, good. And so if you look at n primorial plus 1, it's either a prime number, or if it's not prime, it has to be divisible by a prime that's not on our list. Now, do we agree that n primorial plus 2 is composite? Can you give me a number that divides n primorial plus 2? 2. What about n primorial plus 3? Is that composite? Yes. What divides it? Okay. n primorial plus 4. Is that composite? Yes. And so how high can we go and still have a composite number?
Or sorry.
Well, so can we go to n primorial plus n? Will that still be composite? Because n, if n is prime, great. If n is not prime, it's going to be divisible by prime less than n, which would then divide n primorial. So clearly, at least up to n primorial plus n is prime. I'm sorry, is composite.
Yeah.
So we've just shown, best case is maybe we have a prime here and a prime here. We have a desert of length at least, I think it's like n minus 2. So this is a simple proof that you can have arbitrarily large gaps between primes. This bound sucks. You know, the prime number theorem says there's about x over log x primes up to x. That means the average spacing between primes is of size log x, because average spacing times number of events has to be x. So the average gap between two primes is of size x. N primorial is huge. We're talking about something of size n relative to n primorial. This is insignificant. This is terrible, but it's explicit. I can explicitly tell you there's a gap between primes here. Okay, so again, for today, I am not always the best coder. I'm not always the best at finding these things. There's a real danger sometimes in overthinking these problems. Part of it is I know that as you go further, you're not going to leave your stuff?
I'll come back.
Okay,
Let's
okay.
just take a quick
Yep, that's fine.
phone call.
Okay, so a lot of times when you go, further in these project Euler problems, you actually revisit the problems from the beginning, and they give it to you again with a larger number, so that what you did before doesn't work. And I fooled myself on one of the ones today because of that, as I felt, oh no, it can't be this easy of just do it by brute. No, it's do it by brute force. And they want you to just build up some basic coding skills. And then for some of the later ones, that gets truly challenging. All right, so this is a good place to stop. And we'll stop recording.